Hey everyone, I'm Dylan,
I'm Grant.
I'm Tyler.
and we looked into ski displacement under three-point bending.
All right. So our real world motivation is to model the composite materials that skis are made of and compare the stiffness for the different parts of the ski in order to optimize the design for the type of skiing. Our hypothesis and research question is that the stiffest part of the ski is under the boot, with the tail being the second stiffest and the tip being the least stiff. The independent variables for this are the force applied, which we did 0 to failure, and the ski segment, which includes the tip, under boot, and the tail. And our dependent variable is the deflection.
All right, so here's a little more on our procedure. So at first, we had to make sure the machine is calibrated, and so we used a machine on the ITLL that they actually calibrate for us. So after we confirmed that this was the case, then we could load our skis for three-point bending and run our test, which we later exported the results to MATLAB for analysis.
So here's our test setup. You can see the 3-point bending fixture on the right. It has so there's a force rating of 500 kilonewtons, which works good for a skier, and the support span is 200 millimeters. And the total length of the ski was 170 centimeters, which we cut into different sections, as you can see on the right. And these are all the dimensions we measured in order to calculate the moment of inertia.
All right, so here's a schematic to get a better picture of what our testing looked like. So the first thing we had to do was cut the ski into three segments. So as you can see on the top left, the middle ski had these little yellow supports on them, which we had to take off in order to get a better understanding of its modulus of elasticity with easier geometry to measure, all that kind of stuff. And so after we did this, then we could load the skis into the three-point bending machine, which we later got our results.
So here's the MTS Exceed universal test system that we used in order to run the tests. The test speed we used was 6 millimeters per minute, which was recommended by the ITLL. And here's the vertical test space and frame width. Our skis were cut in order to fit into that space. And also the position resolution was really small, so we did not account for that in our error because it didn't affect it at all. And also this machine is able to be used for composites, which works for the skis. So. And then our sensors that we used were these MTS load cells, which have a capacity of 50 kilonewtons, which works because that's a lot more than the weight of a skier, which is about 608. And they also have these built-in shunt resistors, which verify the accuracy with calibration routines as we collect data. And then this is the digital controller we used for data acquisition. This was built into the machine and in the ITLL setup. It has a sampling frequency up to 2,500 hertz, and we only used 10 hertz sampling frequency, which was enough to prevent aliasing. And it also has 23-bit resolution, and it uses 5,000 hertz closed loop control. And the software that this uses is the MTS Test Suite TW Essential software.
So for our mathematical model for the 3-point bending, we used a simply supported beam with a load in the center. The deflection equation corresponding to that is shown below on the left. In order to solve for the modulus of elasticity, we need the moment of inertia, which is shown as I sub y down below, with the width being h and the thickness of the ski being b. The stiffness of the ski is the change in the load over the change in deflection, which corresponds to the equation shown on the right. Once we gain the modulus of elasticity, we can use a more realistic model for the loads that the actual ski will be in the real world. This has the deflection, theta max, and the shape of the actual beam equation shown below. For a predicted Young's modulus, I took the average of a bunch of different ski materials and found it to be about 80 gigapascals.
All right, so in this video, you can see our test setup. That's the universal test machine connected to the computer that we use to collect the data. And then here are 3 videos from our test. You can kind of hear it clicking when it yields. That's just the material breaking during the test. And then on this next slide, you can see this is it returning back to its original state once we release the load, and you can see that it plastically deformed. It does not come all the way back to the original state.
So here's a few pictures of our testing results. And so this is the ski that deformed the most. And so you can see the middle of this ski, which it's kind of cool actually, because on the bottom side, you can see that the material is a little more flexible as it didn't actually break. And it has these threads as well, which are better for tension, which makes sense. It's at the bottom of the ski. And so at the top for this testing, it's foam and some metal. And so this makes sense because this is better in compression. So when we tested these skis, it formed a little like bump on the top, which showed its compression. And so yeah, this is how it reacted.
So for our experimental results, the graphs of the 3 load versus deflections from our machine test are shown on the right. Each has a point which corresponds to the fracture point where it actually yielded. The equations for the linear fits of each section is shown below as well on each line. And these are how we back solved for the modulus of elasticity. The inverse of those slopes are the stiffness, which are shown on the left, as well as the modulus of elasticity, as well as the max deflection and fracture points. So for our predicted E value of 80 gigapascals, this is compared to the linear fits lines, which are shown as solid lines on the plot on the right, and the 80 gigapascal lines are shown as the dotted lines on the right. We found the 80 gigapascals to be too high because our actual range of E value was between 10.14 and 33.34 gigapascals. So we were actually predicting a ski that was a lot more stiff than what we actually found was true.
All right, so here's our uncertainty analysis. So our 3 uncertainties that we measured were length, width, and thickness. And so this is because we used a caliber to take these measurements. And so, it only has so much resolution. And so that was the closest we could get it. And so using that uncertainty propagation algorithm to the right, in MATLAB, we could get our errors, which we got a minimum error of 0.4% and a maximum error of 2.7%.
So for our two-way ANOVA test, we have 2 factors, which is the section of the ski and the load at which the ski is experiencing. For each pair, we only have 1 data point, so we were unable to get an interaction p-value. However, looking at the interaction plot shown on the right, we see that all 3 points and lines would actually end up intersecting at some point, so there is interaction between the 2 factors. This is a graph of the tip and the tail deflection for the fixed end model. The deflection curves, load versus displacement is shown on the left, and the actual shape of what the ski would look like is shown on the right. And you can see that the ski at the tip deflects a little more with an average human load than the tail actually does.
All right, so in conclusion, our hypothesis agreed with the results. The tip was the least stiff, with the tail being the second stiffest and under the boot being the most stiff. Possible reasons for the manufacturer designing the ski this way is because the binding is mounted under the boot. So if you have the binding in the middle, you don't want your ski like bending and pushing into your foot. It also, if it's stiffer in the middle, you're able to hold an edge better, and it's more important to hold an edge at that point on the ski. Also, having a flexible tip allows for your skis to pop up and stay above the snow, especially when there's some deep powder. And then also having a more flexible tail and tip allows you to absorb impact when landing jumps. And then some of our recommendations for future work, and if we were to run this test again, is to test multiple samples, which allows for more accurate data, as well as to run a 2-way ANOVA test. We also want to run tests on different types of skis so we can compare those in optimized design. And it would also be really cool to use some different fixturing setups to compare that to our models. And we also would like to apply the load faster, so that way it like more represents real life. Here are references. Yeah, thanks for listening. Hope this helps with optimizing ski design.